for this workshop. I'm very glad you are here in Mexico City, in our institute. It's a bit late, so let's start with Guillermo. Thank you. Okay, thank you very much for coming. I'm going to be talking about the Abelian logic, and the interest for me in this particular logic comes from the fact that it sort of lies, it appears at the intersection of two topics I'm interested in, which is basically relevant logic and fuzzy logics. Okay, Abelian logic can be seen as a kind of fuzzy logic, and it was originally motivated by some research that Bob Meyer was doing and Slaney were doing back in Australia on relevant logic and some motivations having to do with relevant implication and so on. Okay, so let's start. And I'm going to be talking about, in particular, the model theory of Abelian predicate logic. And I should say that this talk is based on a more general paper on a more general topic, namely fuzzy logics, which is joint work with Carles Noguera from the Institute of Automation in the Czech Republic. So let's start. Okay, so let me give you some motivation for fuzzy logic. In the 60s, there was this guy, Seder. There was a rumor recently that he had passed away, but that didn't happen. So it's quite old, but a very important guy. And he came up with these things called fuzzy relations, which are essentially functions that evaluate from some given domain into the interval 0, 1. And then this idea was generalized to an arbitrary lattice by this other person. And the idea behind this is that there are so many graded notions in real life that you want to have a way to model this. Okay, and fuzzy relations are just ways to do that kind of stuff. And they've got a bunch of applications in computer science. For instance, one particular application, we could be trying to model the degree of certainty of a certain medical diagnosis, which is something that some colleagues in Linz did at some point. Okay, so a more technical motivation would be in the area of constraint satisfaction problems. These are problems in computer science which have received a lot of attention in the last few years. And in particular, these fuzzy relations can be related to the so-called weighted constraint satisfaction problem, where you try to find a solution to a bunch of constraints, but these constraints have degrees. They are not what are called hard constraints, but soft constraints. And in particular, there is some work done by Rossi, this person, very important person, and from the field of substructural logics and fuzzy logic and so on. And he realized that, in fact, we can encode these weighted constraint satisfaction problems in the setting of fuzzy predicate logics. Okay, so what I'm going to be talking about is essentially fuzzy model theory, which is a general study of the construction and classifications of systems of fuzzy relations. So you've got a bunch of fuzzy relations. In this case, by fuzzy relation, I mean some relation such that it's evaluated, it's a function that goes from some domain into some linearly ordered lattice, residuated lattice in particular. So yeah, the field was originally started more or less in a systematic way, at least, by Peter Sintula and Peter Hager in a JSL paper from 2006. So this is why we should care about this stuff, essentially. So let's see. And the aim of the talk will be to show how to construct models where lots of things happen, right? Lots of types are satisfied. We will get to what a type is in a few minutes. And models where very few of them are satisfied, are realized in this case, in the context of Abelian logics. So let's get to what Abelian logic is. Okay. Before we get into the language, let me say something about Abelian logic. Abelian logic is essentially what you get once you look at the following structures. So I'm not going to be particularly interested in the axiomatizations of these things. That's not my focus. I'm more interested in semantics and so on. But if you're interested in the axiomatization, Abelian logic is what you get by looking at the relevant logic RW, which is a relevant logic R minus contraction, and then you substitute the double negation axiom for a principle that says this. Yeah. So now you see why that would be a contra-classical logic, right there, because this thing, because of course consistency of classical logic, you add this on the whole thing.
Guillermo, how are we to read that?
Okay, so yeah, so this would be, yes, I guess this implies this.
That's not the Abelian axiom.
Isn't?
No, it's so it's arrow B, right? That's all.
Arrow B.
All left nested is the Abelian axiom.
Okay, yeah.
So this just says that the arrow is the biconditional or something.
Yeah. Okay. Okay. Yes. Awesome. Okay, so then I guess this thing?
No, all left nested.
Everything left nested. So what do you mean? Left nested. Okay.
Yeah. The exact opposite of that.
Yeah. Okay, like
A, B. Yes.
And then
right parenthesis after the B.
Right. It's just double negation.
Yep. Yeah, it's double negation
Okay.
elimination.
Yeah. Okay.
But with B instead of falsum.
Okay. Cool. Okay, so that's the
That's the usual Abelian.
Okay. Yeah. Cool. So so that's it. But as I said, and as you can see, I'm not really interested in the conversation. So so this is the semantics, which is what I'm actually interested in. So you start with a group, right? So what's a group? So we start with some set G, so we got one operation, we're gonna do it additively, but we could do it multiplicatively as well, that's not gonna be an issue. And then we have an inversion operation, and then we have an identity. So in case, I mean, the group in particular has to be Abelian, which means that this operation has to be commutative. So you will have that this is just the same, right? And what we want to do is try to find a way to interpret in Abelian logic. We want to find a way to interpret, given a group like this, we want to give an order to the group, right? A lattice order to the group. So what we do is that, let's say we add some lattice operations. In fact, this one is not particularly necessary, but still. So this is just going to be the lattice operations that will give you an order for this thing, and of course the order, as always, will be defined in the standard way, let's say, and this is less than or equal to b, right? So what we want to do is guarantee that there is some monotonicity between this additive operation of the group and this order. So what we add is the principle that this operation distributes over this junction, right, over the join operation, so of the lattice. So that would say something like A plus B or C is identical to A plus B or A plus C, right? So this gives you a monotonicity property for this ordering, and we can show that. Let's do that real quick. If I can do it. Okay. So let's start with the assumption that A less than or equal to B, so that means that A of B is just B, right? And we want to establish that, in fact, A plus C Z less than or equal to B plus Z. You unpack this, and that says what that A plus Z or B plus Z equals B plus Z. Okay, and the way to do this is that we look at this equality right here, given this assumption. So, no, okay, so I'm running out of space. So what we do is that we unpack this. This is something like Z plus, and recall that the group is Abelian, so these two things are just the same as the other way around. So Z plus A O B equals, right? B plus Z, and our assumption is that A of B, right, equals B, so Z plus B equals B plus Z, and that's true because of the Abelian axiom. So in fact, we get that there is a monotonicity property for this operation with respect to this lattice order that we added to the thing, right? So this is what this axiom says. So once we do this, we get the standard semantics for Abelian logic, and the way you interpret the connectives is that, of course, the classical lattice connectives are interpreted in this standard way, the obvious one. Negation, well, not exactly, but this inversion operation is something like negation. And then the important thing is that implication, which is what we are concerned with, is just going to be A plus B, the inverse of A plus B. Okay? And the way you evaluate the truth of a given formula in this structure is just that you say that 0 has to be less than or equal to the value of that given formula phi, let's say the value phi, and then you say that that formula holds there. And in particular, there is something interesting as well. So this operation, this additive operation, as you can see, plays the role of a fission operation, which is the intentional version of a disjunction. So you might ask, well, can we also define an intentional version of a conjunction? And indeed you can, but what happens is an interesting thing. You define it like this, let's say, right? And you say that this is going to be fusion, an intentional conjunction. But because of properties of group theory, very elementary properties. Okay, so one theorem of group theory says that the inverse operation distributes over this addition function, right? So why is that? Well, the way you prove that is because the inverses are unique in a group. So it suffices to show that in order to show that this thing distributes, in order to show that this law holds in group theory, let's say, all you need to do is show that this thing is actually an inverse for A plus B, right? And that's not so difficult to do. And an inverse means that, well, this is, in case you, right? That when you get this, then you get the identity, something. So, okay, so what happens is that you distribute here, right? Plus, minus B. But there is also an elementary theorem from group theory that says that this operation, this inversion operation is an involution, which basically says that this is always going to hold. Okay? So then you get that, well, this happens. Right? It just collapses into this additive operation. And then in particular, this structure is an example of what's called a residuated lattice. Because we have a residuation law holding here. This is the residuation law. Oops. And so we have defined, okay, let's do it like B here. Less than or equal to minus A plus Z. I guess that should work. Okay, so one direction, let's say. Let's start here. I have an hour, so that's why I'm doing this sort of thing. B of Z is just Z, right? And we want to show that B of minus A plus Z, right? It's just what? Minus A plus Z. Okay, so this is our assumption for the first direction. And then we need to, what can we do here? So we add some negation using these principle. Yeah, maybe let's add some A on this side. See what happens. Actually, let me see. Is it that in line? Yes. Jesus. Okay, so okay, so let's distribute the plus minus a. This is just, I mean, this thing is just identical to this, right? Or b plus right? And then, and we need to show that this is identical to minus this is not here. This is oh, okay, yeah, sorry. Okay, wait, did I? Okay, yeah. So b plus 0, yeah, so okay, so b plus 0 is just minus 7 minus a. No, that was. I totally forgot how to prove this.
Can you distribute on the left for some time?
Yeah, no, but I distributed. No, but I have it here. I forgot my own notes, what they said. This is just this. This is A, B. This is just assumption there. Maybe change here, substitute set for some of the. Yeah, let's try that. Let me see if I can do that. Substituting here, b or minus a plus b. So no, that's way too complicated. It was much simpler than that. And it's kind of obvious. It's just that I'm not seeing it right now. This is what I want to get. Maybe add some things. Oh, okay, yeah. Oh, wait. Yes, I guess. Sorry about that. Yes, I guess I need to add minus a. Some, yeah, okay. Let's add minus a over here. A plus b. So, minus a plus a or something, and then that's equal a plus z. Sorry, maybe that should work perhaps. So then distributing here, we get what? Yeah. So minus a plus a plus b, right? And then o, yes, a minus a plus z. Yes, okay, now we are getting where we wanted, yes, more or less this. And then, okay, so then here, because this is a group, right? So this thing is going to be associative, so then you get a minus a. Yeah, I knew this was simple enough. Plus b, right? O minus a plus z equals minus a plus z. And then these things, they just turn into the identity, right? Plus b, O minus a plus z equals minus a plus z. So this turns into what? B, right? B, O. equals B, right? And that's exactly what we wanted, right? So then we get residuation in that direction, and we can do an analogous thing in the other direction as well. And that gives us that this is a residuated lattice. Okay, so that's another property. And yeah, that's pretty interesting. So what we can do now is introduce a quantification language, okay, where we have the standard thing. So you've got a bunch of relation symbols, bottom, top, the lattice operations, and then you have this implication that we already saw how to define on the groups and everything. And then we have quantifiers. And now I have to do something else because it's necessary for my purposes. I need to look at the reason why Abelian logic is a fuzzy logic is because it's complete with respect to the linearly ordered Abelian lattice order groups, essentially. So this is something that you can even see in the original paper by Meyer and Slaney. So they have a completeness theorem that essentially looks at a linearly ordered model. So whenever you have a logic which is based on a residuated lattice, and it's complete with respect to its linearly ordered models, essentially that's going to be called a fuzzy logic. Okay, according to some people. Not everyone agrees, but the idea essentially is that that's one of the fundamental properties that the real numbers have that allows you to interpret fuzzy logics on the real numbers, essentially. Okay, so Abelian logic is one such logic. It's actually a fuzzy logic. So, and this is not surprising, and it's well known. And George Metcalfe has done a bunch of studies about this topic of Abelian logic, and you can even find it in the handbook of fuzzy logic. So it's pretty standard. So,
just a question so far in terms of the constraints connecting the Abelian group to the lattice order.
Yeah.
So it's just a lattice with top and bottom. Do we need it to be a bounded lattice?
Okay, so normally you don't need top and bottom, but I do need top and bottom. So I'm gonna take a bounded lattice.
And so do you need an additional constraint on the interaction between plus and bottom, the way you normally do in substructural logics?
Between, you mean between the identity or between these two?
Between plus and bottom.
Yeah.
Right, so bottom's effectively a zero area join.
Yeah, but
the
that's
distribution condition for bottom won't follow from the one for binary join.
Yeah, but that's not always necessary.
Okay.
I mean, in substructural logics, if you look at the weakest examples, right? Let's say an full number algebra. So you might have a bounded algebra where actually the monoid thing has nothing to do with the bottom thing. So that's not
okay. So you are imposing just the binary distribution and not anything else.
Exactly. I'm not going to be concerned. I mean, you could do that, but I don't see that that's necessary for my purposes. In fact, for instance, you have in fuzzy logic you have something called uninom logic, and uninom logic is normally, if you look at say an MTL algebra, which is like one of the most basic general fuzzy algebra that you can find. Something like that. You don't really need to have interaction between bottom and this monoid operator, which normally that would be like a bottom or a top, depending on how you present it. But in that setting, in uninom logic, you don't need that. And then you don't get weakening, you don't get a bunch of things, right? It's much weaker than any of that. So, yeah, so. Yeah.
Okay, well, my question has nothing to do with weakening. It's not.
Yeah, I know, but what I'm saying is that in uninom logics, you get less principles than you would get in traditional fuzzy logics, right? Let's say in the so-called co-fuzzy logics.
Maybe we can talk about this afterwards.
Yeah, but no, I don't see that you need it actually, and you can have those things independently. I mean, it's not particularly weird, I guess. It's sort of standard. You can add those top and bottom operators. In fact, any lattice can be turned into one of those, right? So it's known that you can get a completeness theorem for even full number calculus into bounded lattices. And you don't do it by changing the monoid operator or anything like that. You just add top and bottoms to the lattice, right? And then in that setting, yeah, you don't need any interaction, even though you have those two things. And in particular, it's not so surprising because then what do? Well, you just add the axiom that says, well, bottom implies everything, right? And then everything is implied by top, everything implies top. So yeah, that's it. That's okay. And in fact, this happens in relevant logics as well. So there are very weak logics that Gabay studied in his book. What's it called? Something on temporal thing. I mean, a book where he looks at some really weak relevant logics where in fact you don't have any theorems, right? Other than maybe if you have these operators, things like this stuff. So yeah, I don't know that that's particularly problematic. But I don't know, it depends on what you want.
I mean, so the constraint I have in mind is you need to do all kinds of, if you want to do ideal constructions over this, and right, it's used in a lot of those kinds of algebraic manipulations.
Yeah,
If you don't want to do those, then it won't matter at all.
Exactly.
Maybe it won't matter, I don't know, right? But if you do want to do ideal constructions and so on, you need this extra.
Yeah, that might be so, but the point is just that if you just want to have, again, the purpose, the reason why I want this is not because bottom and top are playing any super important role. They are playing one role, but what I want to be able to say essentially is that some formula is actually absolutely false, right? So nothing other than that. So, but I don't need it to interact that well, I guess, with the other things. So, because the principles that I'm using are pretty general, I would argue. But yes, that's one thing. So, okay, so again, we are going to be looking this time at the linearly ordered bounded lattice. So, bounded again, this means according to the order of the lattice, this element is at the bottom and this element is at the top. Okay, according to the order of the lattice. So, what we can do then is define a notion of truth. This is something that was done in Meyer's paper with Slaney as well. But of course, they didn't use this particular terminology because this comes from fuzzy logic, which essentially says, well, look, we want to evaluate the quantifiers in the obvious way, namely using Infima and Suprema. Okay, but this is not always the case. These kind of things, they don't always exist, the Infima and Suprema, in a given structure. And the structure in this case, again, since we are looking at the quantificational case, you are going to start with some domain, and you're going to evaluate relations in the algebra, essentially, in the lattice that you're looking at. In this case, these are the original lattices. So what you do is that, and then you build formulas in the standard, the value of the formulas in the standard way, using the interpretation of the connectives that we discussed. So after you have that, then in particular you want to look at structures which are, in the terminology of fuzzy logic, safe to evaluate in. This means that for any collection of values that are values of a given formula, you are going to have Infima and Suprema. So you are going to be able to evaluate the quantifiers. Okay. So again, this was also in the original paper by Meyer and Slaney, but they use a different terminology. And we are interested in these things because, of course, when it comes to completeness and all of these purposes, it's nice to have this property of the models. In particular, in Slaney and Meyer's paper, I guess they call them partial. The ones where this doesn't happen, they call them partially evaluated models or something, because not all formulas can be evaluated. Right? Not all formulas take a value. So, yes. So we do that, and well, in particular, there is another property. Yeah, so the truth value in the quantifiers in the obvious way, but there is another property that we kind of need, which is, let's see if we have it here, exhaustive. Yeah, so the model is exhaustive if every element of the algebra is actually the value of some formula. In particular, one example of an exhaustive model would be the Henke model for your completeness proof. Okay, because since you're looking at the Lindemann algebra, in that setting, you just construct the Lindemann algebra, and you take that to be your lattice and whatnot. Then, of course, you will get exhaustiveness in a sort of trivial way, right? So it's not so difficult to find those examples. So we want to look at such models, and then again, of course, all of this. If you look at classical logic, it's all exhaustive and it's all safe and whatever, right? There is no issue. Well, and another property, this zero witness property, which essentially says, well, look, if I have some existential quantifier, I can witness it in my model by some element of my model, essentially. So that's also kind of important. And then we are going to look at tableaus. What's a tableau? Well, a pair of theories, collections of formulas, such that when we want to define satisfaction for a given tableau, we do it in this way. We say that that tableau, so what's going to lie in here, it's going to be essentially everything that we want to make, that we want to satisfy, let's say. In particular, this symbol here means essentially that the value of every formula in T is just bigger than or equal to 0. Right? So we want to use the truth definition, and then we define satisfaction by using this notion of truth in a model, which is being less than or bigger than or equal to 0. So yeah, so a tableau is satisfying a given model if and only if we have this, right? So everything that lives in T is actually satisfied, and everything that lives in U is actually not satisfied, right? So it's just falsified. So, okay. Yeah, so then again, we can define a sort of consequence relation or something like that, where you essentially say, well, look, if this tableau holds in a given model, then we want that phi also holds in that model in particular, right? So we can do that in a sort of standard way as well. And yeah, so we introduce this notion of a tableau inconsistent if and only if the lattice disjunction of some finite subset of the U is no. It's not provable. So you cannot do it for any finite subset of the U. And then we are going to say that that tableau is consistent. Because, of course, if you could do it, then there would be no way for you to find a model where this tableau is satisfied, right? Because then something in U would have to be true as well. And we want to falsify everything in U. Yeah, so this is pretty standard. The notion, this terminology of tableau was, as far as I know, appears in Chagov's and Shakarevsko's book on modal logic. They use it for intuitionistic logic. This has been called pairs of theories or something like that by Reston as well. Maximova calls it theories in the context of intuitionistic logic. But I find it that tableau is a bit more, yeah, I would say enlightening or something, because it gives you the impression that you're actually working with some tableau, right? So you're trying to make everything true on this side, falsifying on this side, right? If you work with tableaus, you would see, like traditional tableaus at least, you will see that that's what's going on, and that's where the terminology comes from. So then we've got the more existent theorem, which says, well, if I've got a consistent tableau, certainly I can find a model for it, right? A model satisfying that particular tableau. That's not so surprising. And then we got, in this particular setting of tableaus, I don't like to talk about compactness, because in fact, I don't know that you can prove that property I'm interested in, at least, it's actually a compactness property. I'm not sure that's the case. It depends on the topology that you define, but at least defining on the obvious topology, that's not a compactness property, but a different kind of property, of topological property, which is called, yeah, well, I'm calling it almost strongly as close. Strongly as close, it's certainly topological property. Almost as strongly as close, it's the way I'm calling this particular property, which basically says, well, every family of basic open sets with a finite intersection property has a non-empty intersection. Okay. So, if given that topological property, that's the logical analog of that topological property is essentially this theorem, which is a sort of, it's got a sort of compactness flavor to it. Certainly, you can do the things that you would want to do in this setting with the compactness property, with some limitations, of course. Because we are now, for instance, in particular, you can notice that since we are working with tableaus, you cannot quantify over a tableau. Let's say you cannot put a quantifier over here. So it's not like you can say, well, I can find this x, for instance, you cannot express in a formula that for all x, I can find this tableau holding, or that there is some x such that this tableau holds for that particular x. You cannot express it in a formula, okay? Because we are working with tableaus and you cannot quantify over here, and also there are some trivial reasons having to do with expressivity of these sort of languages that won't allow you to do that. So, okay, so given this fundamental tool, if you know anything about model theory, you will know that this is essentially the core of the subject, the most used theorem in model theory. I mean, compactness, and in this context, this strongly as closeness thing. Okay, so we can introduce some other things, some notation. We will write that. Oh, sorry, this was from the previous talk. Not taking value 1, but what this means is that whenever there is a formula such that it's bigger than or equal to 0 over here, that same formula is also bigger than or equal to 0 in the 2, right? Pretty much what you would expect. And this is just the theory of this is just going to be what the tableau, not the tableau, right? The positive tableau, let's say. The ones that are, the part of the tableau that I solve is true of a given model. Right? Because of course, if you look at the given model, you can find the tableau for that particular model, which is just everything that holds and everything that is falsified. So you put them, everything that holds on the left, everything that's falsified on the right, and then you've got your tableau, the complete tableau, if you will, of that particular model. Okay? But in this case, we're just looking at the things that hold on the right. Right? So in fact, here we should have like a positive sign. So yeah, so we can establish a theorem which is an analog of a classical model theoretic theorem, which is called elementary amalgamation. In this case, by elementary, of course, I mean in the language of fuzzy logic, which is not the same as first order logic, but it's just the analog of that. So yeah, so this elementary amalgamation theorem says, well, look, if we have this situation holding, right, so everything that holds in the first model also holds in V2, then we can find a third structure, right, which is a sort of amalgam of the two, such that, let me see if I've got a picture here. Okay, so I've got a picture, that's much better. So this is going to be elementary, and this map is not necessarily going to be elementary. Okay, so a map in this setting is something else that I should clarify. As you can see, a map is going to be composed of a couple of functions, because you need to be sending things from domains to domains and from lattices to lattices. And of course, you need those maps to interact in a nice way as well, right? So in particular, they need to preserve values. Depending on what formulas you want to preserve, you will want to preserve more or less. In the case of an elementary map, yeah, well, in this case, it's much stronger. But in the case of, let's say, this elementary map, what that says is that everything holding here will hold in here as well. What this one says is something much stronger. This says that there is an embedding. Okay, so this is just a substructure of this thing over here. So on the one hand, these two things would collapse in the case of classical logic, right? So, but in this setting, it's totally different, and you do need those pairs of mappings and so on. So you can build this, and this is particularly useful, and we are going to use it to build saturated models. Well, what's the use of this sort of stuff? Well, when you're trying to build, we'll get to what a saturated model is in a minute, but a saturated model in a nutshell is essentially just something where lots of things are going on when it comes to formulas being satisfied and so on. And the way you build these creatures are by taking unions of models, of chains of models, right? And then you need to be able to build such chains. And the way to do that, one nice way to do this is using this elementary embedding theorem. So, yeah, so this is the basic instruction that you use in this sort of saturated models constructions, which is a chain of models And then you can define the union for these particular non-classical models as well in a more or less standard way. In particular, something interesting is that given that the axiomatizations of these creatures are all universal, so they can all be written with universal formulas alone, then you will get that once I construct the union of these algebras, it's also going to be an algebra of the appropriate sort, because universal formulas are going to be preserved under the union construction in classical model theory. So this is an instance where we use some facts from classical model theory to obtain something in non-classical model theory, essentially. So this construction is fundamental, and the important thing about it is that we can show the so-called Tarski-Bott theorem on unions of models and whatnot, which is this. So for this non-classical version, and this is where we need to use the linearity of the lattice. This is where I need that. Here, without linearity, I don't know how to do this. Okay, so pretty important. Also, the union that you get in the end is also exhaustive, and this is a fundamental construction in model theory, as you could probably know. So yes, pretty important. Also, in fact, in fuzzy logic, you do need to have linearity as well for a sort of different reason, because you want the axiom having to do with distribution of the universal quantifier of this lattice disjunction. Yes, over lattice disjunction. That axiom requires the algebra to be linear in fuzzy logic. Otherwise, you don't get that axiom holding. In this setting, I'm not sure. I didn't check, to be honest. It might be the same thing. It might not be the same thing, but in any case, I do need it for this particular theorem. So, what can I do? Okay, so let's see. Now we are going to. Okay. So this is the notion of a type, essentially. So we are going to be looking at types in this setting of tableaus. Okay, and what the type will be is just some tableau which is consistent with the theory, the full tableau, the complete tableau of the model Bn. Okay, notation here is pretty sloppy actually. So, but this is just a complete tableau. So of this model Bn with respect to this set of parameters A. Right? So because of course types, they can be relativized to sets of parameters as well. So they depending on what you want to do. So what this means is, again, the complete tableau is just everything that's holding in the particular model goes to the left, everything that's failing goes to the right. Okay. So yeah, that's how do we define types.
So the type is just P, just
the type. No, the type would be this.
It's the pair.
Yeah. Okay. Yeah. So yes. So in fact, yeah. I mean, you can build saturated models in this setting in two ways. You can build them for left types, what I call left types, which will be just this, will satisfy, or you can build them for the tableau, right? If you want to do it for left types alone, then you can just use the elementary amalgamation theorem. If you want to do it for the full type, you need to use a different theorem, which was proved by Noguera and Cintula in a paper generalizing Hanking constructions. This is a paper that was published in the Journal of Symbolic Logic, generalizing the Hanking construction for a bunch of abstract algebraic first-order logics as well. And if you use that theorem, then you can get these saturated models for full types, right? Left or right and everything. So yeah, so okay, so this is the left type, as I was saying. So this is empty on the right, so you don't require that anything is falsified. In fact, for me, left types are not so incredibly interesting because when you are in contexts where you don't actually have Boolean negation, I do believe that there is a fundamental lack of expressivity that you need to compensate for, essentially using these kind of techniques to account for falsification where you don't have any way to express falsification in the language. I mean, except for, of course, the extreme way of saying, no, this is absolutely bottom. And then, yeah, that's something that I need to use, but this is not the same as saying that it's just falsified. And in fact, I mean, this is a well-known problem from the philosophy of dialecticism as well. Right? What's it called? The exclusion problem. Anyway, it's a
lot of things.
Yeah, but it's particularly, yeah.
Can I ask?
Yes, because
The idea of having like a verification or falsification type as pairs, is that original to you? Or
no. This is, as I said, this is well known from the literature and intuitionistic logic. And then this also came from Gergestel. He has it in his book, but before that, right? So this is something that you can find in Bob Meyer. But I would say that it first appeared in the setting of intuitionistic logic. That would be my guess, just because it's been around for long. So yes, and it's, I mean, it's a natural thing to consider. Yes. So then, okay. So saturation. So what do we mean by saturation? It essentially means that anything that could potentially be the case will be the case, more or less, something like that. Okay. So what it says is that, well, let's take some set of parameters. So saturation is relativized to cardinals. So we take some set of parameters that has cardinality less than kappa. Then the left type, so you can also forget about the left part of the type. The same thing would hold for a type, right? Not just a left type. So a type or a left type is satisfiable in Bn. Every such type is satisfiable in Bn. And again, a type has to be consistent. So what we are essentially saying is that okay, so let's rush. Okay, so what we can do is that we can build saturated model for any kappa, right? So we can build a successor of kappa saturation model, essentially, right, for any cardinal kappa. And this is something that you can do, not just for left saturated modes, but also for saturated modes alone. For left saturated modes, you use elementary amalgamation theorem. For saturated modes alone, you use Noguera's Cintura theorem. And then one corollary of this is some preservation theorem for existential formulas in the language. The preservation theorem is a theorem characterizing using mappings. It characterizes a fragment of a given language. It says, well, whatever is preserved under this mapping lives in that fragment and vice versa. So you can do the same for universal fragments. For the universal fragment, it's just a matter of changing the appropriate things in the kinds of map. And then, well, you also get a omitting type theorem, which essentially says, well, if a type has a certain characteristic, right, it's unsupported or not, then and your language is countered, this is fundamental. If the language is not countered, you cannot do it. Then you can build a model that omits that type, which means there is no element in the model that will realize that type. Right? So that's it. Model satisfying realizing very few types, and model realizing many types. So that's the talk. Thank you very much for paying attention. Q&As? Anyone? Questions?
I have like
Yeah, of course.
question, but it's more like I'm interested in your exhaustive models. So my question is whether there's been some study on the following class. So let's assume we have like two values or some kind of values. Then I'm also thinking about second order logic. And considering I think I'm interested in the class of models such that of a theory or of a logic.
Yes.
That contain. Sorry, it's a bit hard for me because it's new.
No
I
problem.
just was thinking during the talk, but
An hour and a half, so that's a lot of time.
so the idea is, let's say I have a theory and I have a model, right? And the model can be exhaustive. So the model is exhaustive. So I have an exhaustive model for a theory. And then I consider all the models that have the same values as this one. But they may not be exhaustive.
That have the same values, you mean the same algebra,
It
the same
depends.
lattice?
It depends on the kind of model we are thinking. But yeah, in your case, the same algebra. In my, I'm thinking about second order logic. In my case, for instance, would be like a, for instance, hanging model for second order logic that is exhaustive. And then I consider all the other models that are identical to this, but they make different assignments.
Okay. Yeah, but exhaustive, yeah, yes. So exhaustive in the case of, if you're looking at classical logic, everything is exhaustive model.
No, but I'm thinking about values for the second order variables.
Values for second order variables. Okay, in a Henke model. Okay.
So not
Yeah.
every model. So we are talking about countable models.
Yes.
Right?
Well, I mean, it doesn't have to be countable in my case, but yes, you could. The Henke model would certainly be countable, given that the language is going to be countable.
Exactly.
Yeah.
But then
I mean, my Henke model.
we are also talking, I mean, depending on which theory we're working with over logic, then so basically the sets that we include in the second order model and the second order domain are those that are defined in language. And working with that class of models, I think can give interesting results. So maybe I thought you had something analogous here. You get more, like that class of models is restricted, so you get more consequences, right?
Yeah. So certainly, no, I mean, if you restrict yourself to a given class of model, you will definitely get more principles and stuff.
Yes.
But then the problem is, are you interested in that? I'm not sure. Sometimes you want to have like the most general results possible. In fact, I'm uncomfortable with the fact that I have to put some restrictions, let's say on zero indices and so on. It would be ideal if you didn't have any of those restrictions, I guess. So sometimes having a restricted class of models, that's certainly very interesting. But if you're actually interested, if you're coming from the point of view of the structures themselves, the more general thing might be nice. Also because it will hold for more things that you wouldn't have to force any new principles on your logic and so on. So yeah, that's certainly interesting, but I would ideally want to have less restrictions, I guess. That's exhaustiveness, that's still pretty restrictive account, because so many things could be models according to the account, to this account. And the fact that you have to restrict to just exhaustive models, that's like, and in particular, if you want to link it to applications, let's say in computer science or whatever, most of the times they're not looking at exhaustive models or stuff like that. They're just looking at a bunch of fuzzy relations, they put them together, and they say, let's model this or that. And ideally, you would want to be able to say something meaningful for those people, right? Something that they would say, oh yeah, I kind of like that. That's gonna be hard, because to start with, they don't need that much sophistication in what they do. Computer scientists.
Right.
No, but not in a negative way.
Yeah.
It's just it's not necessary. It's yeah.
So Guillermo, I certainly see the sense in which Abelian logic is fuzzy logic understood a certain way, no problem. But I guess I'm just sort of stepping back, thinking about the title of the workshop,
Contra-Classical.
Philosophy of Contra-Classical. And so I'm wondering whether you have, if the answer is no, that's
The answer
I'm
is
just
really
completely curious. Do you think that this has anything to contribute to a particular conception of contra-classical logics? I see the sense in which it is, as you said, one of the axioms is.
Yeah.
But.
I mean, I didn't remember the axiom correctly, so I could be wrong. Yeah. Well, I guess contra-classical. Well, to start with, contra-classical logics are pretty weird creatures. And I deal with a bunch of weird treasures already, so this is like one step up from that. So I guess that my main concern has been with things that would have some sort of, not practical maybe, but I mean, if you can say something for people who are actually sort of making money, maybe that could be nice. So that's been my focus, I guess, with the whole fuzzy thing or whatever. But with contra-classical logics, yes, I don't know that I would have a lot to say about that on a philosophical basis. Yeah, I guess that the interesting thing for me is that, well, as I said, it's somehow connected to two things I'm interested in: relevant logics and fuzzy logics. And I was kind of curious. I didn't know that when Luis told me, "No, you should look into Abelian logic," and so I had no idea. So yeah, but I guess in my sense, Abelian logic was related to something having to do with negation. He said something like, right, double negation and so on. So he said something like, well, if you're really serious about double negation, yeah, you have to accept this principle, this Abelian axiom. I don't know what that means. I'm serious about double negation, and I don't know that I believe that principle, whatever it is. But yeah, I'm sorry for being.
No, I was just curious. Thank you.
So, two questions. First thing, something. So, as somebody who also pushes on non-classical model theory, I've been getting kind of a niggling concern, something just sort of eating in the back of my head, and about the sort of fundamentality of classical model theory. And I just in dealing with it, and in particular, I guess I start worrying that there's a sense in which all of my models for such and such a non-classical logic are first order structures.
Yeah.
And so there's a sense in which I can take all of the classical model theory theorems, and I can turn my non-classical theorems of model theory into classical instances about the first order structures of Meyer-Slane models.
Yeah.
Something like this. And it seems in many cases you can just piggyback on classical model theory. You could really just, in earnest, to say, I'm going to talk about preservation about these first order structures, which are models for an object. So I was wondering if you had any thoughts about that sort of dilemma, about whether you're doing anything in non-classical model theory, or if there's anything to be gained by just sticking it at that level.
That's a great question. Actually, lots of smart people ask the same question all the time. So it's not just you. So the problem with this sort of stuff, this is something that I've discussed with Carlos Noguera as well. These things, they can be interpreted, as you correctly point out, as first order structures. And in fact, I can translate the language of fuzzy logic, and what I mean with fuzzy logic is any abstract algebraic logic. This is pretty general. This sort of technique of using algebras and evaluating two algebras and so on, right? So this is way more general than just fuzzy stuff. But then what happens is that, in fact, you can embed this into a given first order language. And the way you do that is in the trivial way. Satisfaction clauses become equations, right? And formulas, they become functions, essentially, right? So you have this functional language, you embed everything there, and you can say a bunch of things. Now, what happens in this particular context with this particular kind of results is that I don't reckon that this is a consequence or a corollary of the classical omitted types for a number of reasons. First of all, because the classical omitted types is dealing with, or let's say the saturated types or whatever. It's dealing with full formulas, right? So you need more, a bit more. In this context, I'm just restricting. Maybe it would be a consequence of some restricted version of the theorem, and you would have to prove it sort of independently of the omitting types and the other kind of and the saturation theorem, and you would have to prove it independently, sort of. But that's essentially what we did here. But yes, there is a sense in which I could just take all of this and turn it into a result about the fragment of first order logic, for sure. Yes, absolutely. But then again, there might be some things that might change. For instance, the notion of satisfaction here is not necessarily the notion of satisfaction for first order logic, because it's not the same to say that some formula, let's say, the value of some function is less than or equal to 0. That's a formula in first order logic, right? So that's not saying that that function is not a formula in first order logic. So it's not exactly the same. It's a translation, of course, but it's a translation which is less classical in a sense than, let's say, the translation from modal logics into first order logic, or the translation from any substructural logic into first order logic. When you have possible word semantics, that's what I mean. So when you've got possible word semantics, you can give a translation which is fully classical. There's no weirdness whatsoever. It's just standard first order formula. But in this context, you are looking at algebraic formulas, right? At equations. That's not exactly the same. The notion of satisfaction doesn't coincide. You cannot just say, yes, the notion of satisfaction in this setting is just the classical notion, but with a translation. That's not what's going on. So I would say that I have bigger hopes in this regard for this sort of algebraic logics than I have, let's say, for possible word semantics.
It's hard. I wasn't trying to denigrate it.
No, but it's a good question.
Yeah, I wanted to sort of rewind to the beginning of the talk, think motivationally, think about where you're coming from, why we're looking at this sort of stuff. And ask particularly after the Abelianness of the Abelian logic, right? Because the opening motivation was about fuzziness in this sort of max into 0-1 interval sense. And then you say, okay, an Abelian logic's a fuzzy logic if we understand fuzziness this way. Fair enough, it is. Exactly. But is there the potential for applications of the kinds of structures you're looking at in the sort of weighted constraint satisfaction area that, according to you, motivates thinking about the 0-1 interval? Yeah. So like what's the Abelianness doing for you, or what could it do for you?
That's a good point. I mean, the Abelianness here is just this commutativity thing.
Oh, sure. Like, why are Abelian groups interesting, given the applications that you have in mind?
So, one reason for that, for instance, in the context of fuzzy logics, is the residuation law holds either if you take, I mean, either this form, or it could also hold like this. So if only B, right, less than or equal to, A less than or equal to, A less than or equal to B plus C, okay? So that's I mean, from the algebraic point of view, that's what commutativity.
Okay, so there's where commutativity does.
Yeah.
Well, why are we thinking about groups in this context? Then becomes the question, because you can have all kinds of commutative lattice ordered.
Yeah, exactly. Yes. So
for non-contra-classical logic, that nonetheless will give you that.
Indeed. So this is the thing, right? So groups, I'm not particularly interested in. So this is just one application of a more general thing that was looking at MTL algebras and logic and uninorm algebras. And I realized that, well, in fact, most of the things can also hold for this particular setting because it's general enough. And in the end, this is also fuzzy logic, so it's got a bunch of fuzzy flavor to it. And yes, that's it. But groups in particular, no, nothing particularly specific about that. In fact, in the area of constraint satisfaction, they are not looking at groups. I mean, they might be looking at groups at some given point, but normally the algebra they use to evaluate things on is just some residuated lattice, where you have, yes, commutativity and some properties, not that much more. Right? So it doesn't have to be a group specifically. It could be, but it doesn't have to. Right? So there is nothing particular groups. It's just, I just thought, well, this is sort of a nice application for this particular setting as well. And it shows that what we were doing with Carlos Noguera was general enough that you could apply into a bunch of different things. Right? So, yeah, that's it. Again, a non-interesting answer.
But a very helpful one.
Yeah.
In terms of seeing
Sincere.
how the pieces of it fit together.
Indeed.
My question is connected with the question, and maybe it's a little, it's a more general, but the question is about the relationship between models and application in general in logic. And do you believe that when you describe models, are you describing some application or a general application, a standard application, or you have the possibility to have different applications with only one model?
Yeah, I mean, ideally, I would hope that when you describe a model, eventually you will find some application. That would be my dream, right? But it's okay if that's not the case, actually. In my mind, it's fine. It's just that it's hard to convince people that, hey, you're doing anything worthwhile. I'm cool with that. I'm cool with doing things that are not necessarily, I mean, they're not necessarily gonna change the world. But it's nice when we do have applications, in my mind, yes. So whenever possible, if you can do something that is motivated by something that has already been used. And this is in fact not such a strange idea, I would say. You would find the same thing in classical logic, right? In classical model theory. So what's the reason why they started looking at all of these things? Because they wanted actually to give some feedback, let's say, to mathematics. Let's say if you look at Robinson's work on model theory, it was just a bunch of things that were meant to be applied in algebra, right? And they made life easier to a certain extent in algebra. So that's the kind of motivation that I would like to have. Not always possible, sadly. But yes, I do believe that if you find something, you're looking at some structures, and these structures have been independently motivated, that's really nice. Also because it's easy to apply for projects and stuff like that. You can't do that, right? It seems like that's always helpful. But no, I'm not saying that if you're not doing that. I mean, I've done things where I haven't done that. So I wouldn't be able, I mean, I couldn't say, no, if you do that, then it's just not worthy of my time. That's not what I'm saying at all. I'm just saying that it's nice if we can have models work. Yeah, there are some applications. And I would imagine that most people in this room agree, right? It's such a controversial point, I hope.
Okay, just one more question because we're out of time. Yes, or
No, I think we have time.
Thank you for the talk.
Thank you for the talk. I was trying to follow. I'm not sure I really did it, but I'm interested in preference phenomena, preference logic. Maybe you can use some of these things.
Indeed.
In the Shane's theory of the possibility of partition liberal.
So this is Arrow's.
Yeah. Well, the twist.
Okay, Arrow's theorem with a twist. Okay, I'm learning this stuff.
And I was thinking that in law, you always are looking for exceptions for that rule that from bottom everything follows, especially interpreting political authority in democratic contexts, for example. So if you have preferences like that are incompatible but are politically equally valid, both of them, you need to a rule to block that axiom in particular. And to find exceptions for that axiom, because you can have preferences against human rights and preferences that go well with human rights. And if human rights is the better authority there, democracy as the add or sum of preferences of a certain population would not hold, and that axiom up there would need to be blocked somehow. So this is the case when the majority of people vote for Hitler or something.
Okay, yeah, so that's a good point. But then again, my interest here is actually just technical to some extent. As I said, I just want my language to be able to say that something is definitely not the case at the very least, right? Sometimes that's something that I do need, and unfortunately, this is something that automatically follows from the fact that you're going to have this bounded lattice. And but of course, in original Abelian logic, that's not present. They don't have bottom or top or anything. But then again, my personal conviction is that if you've got a language where you don't have that, that's a very silly language for me. Again, personal conviction for a number of reasons. First of all, because it doesn't have any more theoretic characterization that is even remotely nice. Because anything, I mean, like if you try to give, let's say, a preservation theorem, like I was saying, that you build some map such that you preserve all the formula that you want to preserve, that's not going to hold. That's not going to happen, because then this kind of formula, this is always going to be preserved under any map whatsoever, and your language won't have a way to express that formula. So then you have a crippled language in a fundamental sense, in my mind. But of course, people disagree widely with this. This is my personal conviction. I reckon that if you've got a language that has no nice, more theoretic characterization, what kind of language is that?
Yeah, if you manage to model this kind of reasoning that I'm saying, not the way I'm saying, you can find
But some other,
an
yeah,
application very useful for your modes, I think.
yeah, that would be nice. I mean, and you could do maybe that absurdity thing doesn't necessarily have to be this. This could mean something different in that particular context.
Yes. It was just a follow up on that. It's fine.
No, it's okay.
Okay. So you said that what really interests you is finding models that have applications, and everyone in this room would agree. But as illustrated by this question, I mean, a model will always have applications. That's easy, right? You mean models that have applications
Independently
for things
motivated, yeah.
that make toasters or something like that.
Washing machines, actually. Fuzzy logic. Not toxic. Okay. No, but what I mean is essentially that these things have been independently motivated. The structures, okay? So they've appeared elsewhere somehow, and they have an independent motivation. I'm not talking about necessarily practical applications. Practical applications would be great, awesome, amazing. But it could be purely mathematical applications as well. Okay? And they've been independently motivated, and then I want to try to look at those. That's essentially the same that happens in classical standard model theory. So,
Small point.
yeah, no. But I mean, I guess that's not so controversial, is it? But maybe I don't know, maybe it is.
It shouldn't be controversial that for any model, there's an application of that model.
Yeah, of course. I mean, yes. That's not, no, but I'm saying that you want to look at things that are independently motivated, ideally. If you are doing model theory at least, this is my, yeah.
Okay, so, okay. Well, it has to be with this conversion between structures. So I was wondering, well, as long as you, as the conversion, preserve the intuition behind these logics you're following, what will be the problem with that conversion between structures? I mean, to reduce these structures to first order.
No, yeah, there is no problem. The problem is not that, okay?
Well, I mean, what is the, well, I will hear and then I will.
No, what I said is that I'm not sure that I could get these results as corollaries of the classical ones. I guess that I could write these results as classical results. Yes, that's not controversial. But as corollaries of classical results, not so sure, because the classical results, they assume a bunch more. You would have to look at the restricted versions of such results, and then that would be essentially doing this, which is cool, that's fine. You can also say, I'm just working in a fragment of classical model theory, and I'm doing something that is not exactly what they're doing, but kind of looks like it.
Okay. The consequence relation will change in this conversion.
Your preservation of one relation you're talking about, I think, is what he wants to know.
Yeah, but it depends on what you mean by the consequence relation. I guess. Because if you mean, we can mean several things, as I said, right? So my definition of satisfaction is different from the classical definition of satisfaction. So then, even if I translate it, I wouldn't get that those two definitions are equivalent as you get in classical model logic, let's say, and cryptic semantics. The definition of satisfaction is the same as in cryptic semantics when you look at the translation. But in this context, that wouldn't be the case. It would be an equation. My formula being satisfied would mean that certain equation holds, but that's not what it means.
And you will lose some expressive power.
No, I don't think so. No. The expressive power will remain the same. It depends on what you want to express, right? But if you are trying to express the same things about the things that non-classically I was talking about, of course, if you go to the classical setting, in fact, if you enhance the language, let's say, you will be able to express even more. Yeah. So
So this, let's examine.